Okay, hi guys. So in this lecture, we'll be seeing some of the questions on Heisenberg uncertainty principle, so as to get some practice on the same. So you have to calculate the wavelength of the particle in the following two cases. First is you have to calculate the wavelength associated with uh, wavelength associated with a 66.3 gram tennis ball traveling at 50 meter per second. Okay, so for this case we would be having that lambda is nothing but h upon mv, or h upon momentum. H is nothing but 6.6 into 10 to the power minus 34. M is 66.3 grams. Okay, so 66.3 into 10 to the power minus 3, and velocity is 50 meter per second. So you can easily calculate it, and you would find out that wavelength should be equal to 20 to the power minus 34 meters. Second, you have to calculate the wavelength associated with a particle moving at 66.3 meter per second. Okay, so in this case a particle, let's say a particle was electron. Okay, so the wavelength associated with that would be again lambda equals to h upon mv. H is 6.6 into 10 to the power minus 34. M is again 9.1 into 10 to the power minus 31. Velocity is 66.3. So let's calculate the value. It should come out to be 10 to the power minus 4 by 9 meters. Okay, so next question is you have to calculate de Broglie's wavelength of an electron according so you have to calculate the de Broglie wavelength of an electron which is subjected to a potential difference of 9.375 volt. So calculate de Broglie wavelength of electron having potential difference, or V, of 9.375 volt. Okay, so we know that we have already have a shortcut for calculating the wavelength of electron at a particular volt. So this should be this is in angstrom, don't forget the unit. Volt is 3 point, a potential difference is 3.75, 9.375 angstrom, so this should be 4 angstrom. Okay, next you have to calculate the uncertainty in position of an electron which is moving with 6.62 into 10 to the power 4 plus minus 1% meter per second. Okay, so or rather let's say this is for 6.6 into 10 to the power 6. Okay, so what would be the delta V? So we know that it is plus minus 1%. So 6.62 when subjected to uncertainty of 1% would give us delta V as 6.62 into 10 to the power 4 meter per second is the delta V. Okay, now we know that by Heisenberg uncertainty principle, delta x into delta V should be greater than h upon 4 pi m. Okay, just putting the value of delta V here, we know the value of hm here, so delta x can be easily calculated. So delta x should be greater than 6.6 into 10 to the power minus 34 upon 4 pi mv, which should be equal to 6.6 into 10 to the power minus 34 upon 4 pi. Mass of electron is again 9.1 into 10 to the power minus 31, and V is again delta V, rather this is delta V, not V. Delta V is again 6.62 into 10 to the power 4. So just calculate all of this value, and delta x should come out to be greater than or equals to. So I'll leave this as a homework. Okay, just calculate this value using calculator and you are done. But please learn to how to do quick calculation without using calculator, so it would be really helpful for your examination perspective as well. So if the next question is, if the uncertainty in position of an electron is 1 by 3 into 10 to the power minus 10 meter, and what is the uncertainty in velocity? So again, using the same formula, delta x into delta v should be greater than h upon 2 pi m, or rather not 2 pi m, 4 pi m. Okay, so again putting the values of all the required fields here, so calculate the value of delta v here. Okay, so delta x is given, which is 1 by 3 into 10 to the power minus 10. Delta v has to be calculated, that should be greater than 6.6 into 10 to the power minus 34 upon 4 into 3.14 into mass of electron is 9.1 into 10 to the power minus 31 kgs. So now from here delta v can be calculated, and the answer this time I am giving you should be greater than 1.75 into 10 to the power 8 meter per second. So this should be the answer here. Okay, so this is the minimum uncertainty in velocity. Okay, let's see some notes on the dual nature of electron. So dual nature of electron is actually caused by, first, the movement of electrons, or rather a moving electron will behave, or rather will have a wave nature. Electron would have a wave nature. And secondly, electron during striking or hitting something, striking electron would have a particle nature. Okay, so let's actually go and see our next concept, which is bond energy or enthalpy. Okay, so here we represent enthalpy with H, and delta H would be change in enthalpy. And this can also be written as heat absorbed or released at constant pressure. At constant pressure. Okay, so let's say if delta H is x kilojoule per mole, and if energy is absorbed, then obviously delta H should be greater than 0, or x should be greater than 0, and if the energy is released, then delta H would be less than 0. Okay, so we'll end with this in this lecture. In the next lecture we'll be seeing bond energy and some examples of photochemical reactions. So till then, good luck and goodbye.